I should just
So,
say I am, as I said, a kind of dinosaur of technology, so I don't have slides.
yep.
I have a paper that I wrote uh, called Abstract and Variable Sets of Category Theory that was actually written a few years ago. It was in a volume. I've never actually delivered this as a lecture before. It was published,
Well,
volume of
so
category theory in Italy by a collection of papers. You may have seen them by edited by John Domenico Sica, who doesn't do this sort of work. I'd like to, what I'll do, the paper isn't very long. I will use it as a basis for what I'm going to say. I'll read some of it and try to convey, but I don't have slides. I never got that far. The only thing I have were what are
it's
called
okay. It's okay.
limited.
So, dear friends and colleagues, we're pleased to introduce Professor Bell, who is giving a talk today. So, Professor Bell, thank you for coming and accepting our invitation. So, I think we can start.
All right. Well, I just say that I was very pleasantly surprised to receive an invitation from Moskva. You know, and I didn't know that there was. I knew, of course, that lots of work in mathematical logic had been done in Russia, and then when it was the Soviet Union too. But I hadn't heard of this. This the new university was relatively new there, so I was very pleased.
Yep. And the topic is abstract and variable sets
Absolutely,
in category theory. So,
category theory. Yeah, that's
thank you.
right. Okay. Well, in 1895, Cantor gave a definitive formulation of the concept of set. She called a Menge, to wit, a collection to the whole of definite, well differentiated objects of our intuition or thought. Let's call this notion a concrete set. More than a decade earlier, Cantor had introduced the concept of cardinal number, cardinal Zahl, by appeal to a process of abstraction, which was of course objected to by so many, particularly Zumelo, who didn't like it. Anyway, here's Cantor's definition of a previous definition of a cardinal number. Let M be a given set, thought of as a thing itself, and consisting of definite, well differentiated concrete things or abstract concepts, which are called the elements of the set. If we abstract not only from the nature of the elements, but also from the order in which they are given, then there arises in us a definite general concept, which I call the power or the cardinal number belonging to him. Well, that was his earlier definition of cardinal number. As this quotation shows, one would be justified in calling abstract sets what Cantor called cardinal numbers. Now, this use of the term abstract set is due to, as so many things in category theory, and in this approach to foundations of mathematics, to Bill Lawvere from some time ago. Now, it's interesting to note, I just noted the difference between abstract sets and concrete sets. Now, if you go to Lawvere's usage, or the usage I'm introducing here for abstract sets, it contrasts strikingly with, let's say, the use of the term abstract set by Fraenkel, for instance, in his textbook on abstract, what he calls abstract set theory. He says, whatever one does not care about what the nature of the members of the set may be, one speaks of an abstract set. Well, actually, Frankel's abstraction in this case is better described as indifferent. It's not abstraction in the sense that I'm using it here. Now, I call it concrete sets because, after all, the usual notion of set consists of any object, abstract maybe, but also concrete things. In fact, the striking things about set theory in this kind of informal sense is that the objects or the of set theory the entities treated in set theory are kind of mixed bag. You could put abstract concepts in and lump them in with anything you like to form a set. So the term abstract set I want to use here in a rather more precise sense. In fact, the sense that really that Cantor used it, although there were difficulties with the notion. Anyway, we can say from Cantor's own quotation that one would be justified in calling abstract sets what Cantor termed cardinal numbers. An abstract set may be considered as what arises from a concrete set, where each element has been purged of all intrinsic qualities, apart from the quality which distinguishes that element from the rest. An elusive notion, you might say, but anyway. An abstract set is an image of pure discreetness, an embodiment of raw plurality. In short, it is an assemblage of featureless but nevertheless distinct dots or motes, if you like. The sole intrinsic attribute of an abstract set is the number of its elements. Now, it's interesting, perhaps, to note here, this, it's been pointed out by various commentators, that this idea is close to the ancient Greek idea of the number, an arithmos, which was a kind of raw plurality of things. Well, a plurality of units. Well, what were these units? Well, of course, the notion of a unit is a very interesting one, and we think back, of course, to Frege's famous definition of or identification of the notion of a unit as a concept. Okay. And the sole intrinsic attribute, really, of an abstract set is really its number, the number of things in it, which is, as I said, very close to the idea of the Greek arithmos, which they meant plurality of units. Anyway, concrete sets are typically obtained, if you go back to concrete sets, typically obtained as extensions of attributes. Thus, to be a member of a concrete set C is precisely to possess a certain attribute A. In short, be an A. Well, that's of course why Peano introduced the epsilon symbol for membership, because it's Greek short for Greek este, of course, means is. Of course, I should just mention that it's true. Set theory, the usual formulation of set theory, is as extensions of attributes. If you look at any of the standard set theories, Zermelo's set theory, Zermelo-Fraenkel, and so on. However, of course, there still is the notion that sort of underlies the idea of a combinatorial set, that is a set obtained by gathering elements together. Now, that's a different notion, actually. And there's been, of course, a fair amount of philosophical discussion as to the difference between a concrete set as an extension of an attribute, that is, as a collection of all objects that actually satisfy or have a given prescribed attribute, on the one hand, and a set as a collection of things which we gather and are gathered up in some way and stuck in a bag, if you like. The identity of the concrete set C is completely determined by the attribute defining it. This is the action of extensionality, of course, in set theory. As an embodiment of the relation between object and attribute, membership actually plays a central role in concrete set theory. Indeed, the usual acting sets for set theory, such as Zermelo-Fraenkel and take membership as the sole primitive relation. Concrete set theory may be seen as a theory of extensions of attributes. By contrast, an abstract set cannot be regarded as an extension of an attribute. It's a sole attribute, so to speak, possessed by the featureless dots, to which we shall still refer as elements, making up an abstract set, is that of bare distinguishability from its fellows. Whatever abstract set theory is, it cannot be a theory of extensions of attributes. Indeed, the object-attribute relation, and so a fortiori the membership relation between objects and sets, cannot act as a primitive within the theory of abstract sets. The key property of an abstract set being discreetness, we're led to derive the principles governing abstract sets from this fact. Now, it's characteristic of discrete collections, and so also of abstract sets, that relations between them are reducible to relations between their constituting elements. Now, it's interesting to contrast that with relations between continua, between continuous objects, in which relations can't be reduced to relations between individual elements. In the case, for example, of straight line segments, for example, the relation of being double the length is clearly not reducible to any relation between points or elements, which of course is a source of lots of little paradoxes, of course. So the foundations of geometry are where continuous objects are actually reduced to points. In the case of continua and geometric objects generally, the relevant relation takes the form of mappings. Well, that's, of course, where category theory is going to come in. In the case of the continuous, trying to axiomatize the continuous as well. However, I'm not logically concerned with that here. I will come up to towards the end of my talk. Okay. Construed in this way, relations between abstract sets provide a natural first basis on which to build the theory thereof. So we conceive the relation R between two abstract sets X and Y as correlating some of, maybe all of them, but some of anyway, the elements of the set X with the elements of the set Y. Okay. Here, categorical ideas can first be glimpsed, for relations can be composed in the evident way. So that abstract sets and relations between them form a category, the category of sets and relations, which I'll just call rel. In fact, rel, I mean, you might think that would be the central category in the categorical approach to set theory, but it isn't, of course. I'm sure you know from working with Thomas's and categorical set theory. But anyway, in fact, rel does not play a central role in the categorical approach to set theory because relations, at least this is one reason I'm going to give. They really have too much specific structure. They can, for example, be intersected and inverted. Right? You can intersect two relations and you can invert them. I mean, the inverse of a relation is always another relation. Category associated with abstract sets. We replace arbitrary relations with maps or functions, if you like, between sets. Here, a map from an abstract set X to an abstract set Y is a relation F between X and Y, which correlates each element of X with a unique element of Y. Of course, that's the familiar notion of a function. In this situation, we write F of X arrow Y, the usual notation, function notation, and the X and Y, of course, are the domain and codomain, respectively, of the function F. Since the composite of two maps is clearly a map, abstract sets and mappings between them form a category set, which is known simply as the category of abstract sets. Now, of course, this is not, is that the same as the category of concrete sets? Well, it isn't, actually, even from a category theoretic point of view. You might, those of you, I'm sure, category theory will know that really, if you want to view it from the point of view of mainstream category theory, the category of abstract set is really a skeleton, if you like, of the category of concrete set. I mean, that's essentially what Cantor's category theoretic point of view, that's essentially what Cantor's cardinal are. Okay. So we have this category just known as the category of abstract set. And so while definitions in concrete set theory are presented in terms of membership and extensions of predicates, so that you can apply logical operations, you see, to these predicates. The usual logical operations and quantifiers can be applied there. In the category of abstract sets, definitions are necessarily formulated in terms of maps and correlations of maps. This is the case in particular for the concept of membership itself. Thus, in set, an element of a set X is defined to be a mapping from a set called 1, right, a terminal a terminal object, category theoretically, to X, where 1 is any set consisting of a single dot. That is satisfying the condition for any set y, there's a unique mapping from any given set y to 1, which is just about that takes the constant value, that particular dot representing the object, the abstract set 1. In categorical terms, 1 is a terminal object set. In set, 1 has the important property of being a separator from maps, in the sense that for any maps F and G with common domain and codomain, if the composites of F and G with an element of the common codomain agree, then F and G are identical. Well, of course, that's just the usual idea that two functions are equal. If for any x in the domain, say F and G, if fx equals gx for all x in the domains of F and G, then F equals G. The empty set, the usual thing, with a zero with a line through it, may be characterized as an initial objective set. That is, for any set Y, there's a unique map from the empty set to Y. Well, everybody is just familiar with that idea. In set, the concept of set inclusion is replaced by that of monic or one-to-one map, where a map is monic if excuse me, if it's left cancelable. So if it's composed with two maps, if its results with two maps F and G composites are equal, then the two maps themselves are equal. A monic to a map is also known as a subobject of Y. Well, I'm going to call it a subobject. Actually, in Thomas theory, it's really an equivalent class and so forth. But never mind, put that aside. Any two-element set 2, right, for the usual written in the usual arithmetical way, 2, characterized categorically as the sum of a pair of ones. To be specific, we may choose 2 to be the set consisting of 0 and 1. Plays the role of a sub, or I mean, I put it that way to make it more familiar in set theoretical terms, but it's really a set with 2 dots. It doesn't matter what. It's just 2 distinct dots. This means that, yes, it plays the role of a sub-object classifier or truth value object in set. This is, of course, in classical set theory we're talking about here. This means that for any set X, maps from X to 2, okay, bivalent maps, correspond naturally to sub-objects of X. Maps from X to 2 correspond to attributes to X. Right, where the map takes the value 1, is all very familiar with the usual characteristic functions, and any attribute is associated with a characteristic function, which takes the value 1 when the element in question has the attribute in question, and 0 if it doesn't, since again we're working with classical usual classical logic that gives you a map defined on the whole of the domain A. So we can think of the members of two as playing role of truth value. 0 is false and 1 is true. Well, of course, again, that's really it's what you do with 2 dots, but you got no way of it's a bit misleading what I said there, because of course in set theory 0 is an empty set, doesn't have any element, and 1 does have an element, but of course you can't make that distinction directly in abstract set theory. It's merely the categorical properties of a two-element object, if you like, that characterize 2, rather than the intrinsic nature, if you like, of the elements of these members of 2 would have in concrete set theory. Okay, along with that, with membership in concrete set theory, the concept of identity or equality of sets essentially defined in terms of membership because of the action of ustensionality, right? Plays a seminal role. In abstract set theory, on the other hand, that is in set, okay, by contrast, it's the equality of maps which is crucial. It is, in fact, taken as a primitive notion. I guess it's just worth mentioning here that in category theory, of course, it's not identity, but identity between objects in category theory is almost irrelevant. It shows up now and then, but none of the basic axioms of category theory, of course, involve identity of objects. That is, if you like, of domains of arrows or maps. It's identity between arrows or maps. That's a primary notion, and that, of course, those are, I'm sure you're familiar with this. You can axiomatize, of course, category theory entirely in terms of maps. You don't really have to mention objects at all. I don't think this is the most convenient way of doing category theory, personally. You'll also find, I think, in one of Peter Johnston's books, he agrees that you can do it. Why do it? It just makes it more difficult. What you could do in principle, you don't necessarily have to do in practice if the principle involve more complicated kind of operations than you would choose in practice. Now, okay. Equality for sets is, to all intents and purposes, replaced by the notion of isomorphism. Of course, we in sets. Well, of course, we're very familiar with that idea in categories. There's been a certain amount of argument, or at least there was, about identity of what the meaning of identity of object really is in a primitive way in category theory. I think all this discussion, by the way, a lot of that now has been completely subsumed, I think, under developments in type theory, where you have enough distinctions that you can make between identity and isomorphism sort of built into the system, which reveals all kinds of new ways of handling the notion of identity, in particular with, say, univalence axiom and homotopy type theory. And I think the type theory really has illuminated, I think, some of the foundations or ideas underlying category theory in a really quite remarkable way. Okay. So, of course, an isomorphism is an invertible map, as we all know. Two abstract sets are isomorphic if there's an invertible map between the two assemblages of dots constituting the two abstract sets. An abstract set is then defined, so to speak, up to isomorphism. The precise identity of the dots composing the set in question being irrelevant. The sole identifying feature is, if you like, the form of the set. Well, this is why Bill Lawvere was, because you know what this is getting to. It's getting to Bill Lawvere's elementary theory of the category of sets, which he formulated long ago, and in which the whole idea really was to replace the idea of content by the idea of form, which of course is the major consideration that he had when he was developing these ideas back in the 60s. Okay. In abstract or categorical set theory, sets are identified not as extensions of predicates, but through the use of the omnipresent categorical concept of adjunction. Now, already you see, you get to, it's true that when there used to be these arguments, well, there still are, and certainly neither category theory nor type theory has replaced good old-fashioned set theory as a standard method working in standard mainstream mathematics. I think that may change, of course, because of the infant computer science, and God knows what AI is going to make of it. So we'll see. Okay. So it's really, if you ask what machinery do you actually have to use in abstract set theory in order to develop what to perform the mathematical operations or logical operations even that you can do in abstract set theory? Well, the answer is you use adjunctions, and as we know, when Saunders Maclean wrote that book, Categories for the Working Mathematician, many years ago now, and at some point in the book, he says, well, you can simply take category theory essentially as a theory of adjunction. Every notion can be represented in some way in category theory as an adjunction of some kind. And it's a remarkable notion, which of course has a perfectly good meaning in classical set theory, but is not a central notion there, but it is, of course, a category. In category theory, in abstract set theory, if you like, the definition of exponentials. In concrete set theory, the exponential b to the a, right, of two sets A and B is defined to be the set whose elements are the functions from A to B, the mappings from A to B. In categorical set theory, b to the a is introduced in terms of an adjunction. That is, the postulation of an appropriately defined natural bijective correspondence for each set x between maps from x to the exponential b to the a and maps from the Cartesian product x cross a to b. Here, x cross a is the Cartesian product of x and a. It's self-defined by means of a similar adjunctive, which I'm sure you're all familiar with, expressing the fact that maps from an arbitrary set y to a cross x are a natural bijective correspondence with pairs of maps from y to x and a. The notion in passing, we note in passing that the relations between x and a, right, can be identified with sub-objects of x cross a. Of course, that's how you get the notion of relation in terms of the standard way of doing this in category theory. Thus defined, right, in terms of adjunction, b to the a is then determined uniquely up to isomorphism, as is a familiar exercise, in books in elementary category theory. So uniquely up to isomorphism, that is, as an assemblage of dots. You see, anything really that's determined uniquely up to isomorphism is really abstract, because it doesn't matter what the elements are. They don't even have to have any individual characteristics. They just have to be differentiated from one another in some way. Well, that was, of course, the part that Zermelo objected to, as he was an editor. He was editor of Cantor's Gesammelt der Werke, and he didn't like this abstraction. He didn't like it either, of course. Frege wrote a commentary on. He thought it was vague, and of course, the objection is it's identity of indiscernibles. I mean, if these dots or whatever you call them, Cantor called them ones. Lauter Einstein, he called them. If these units, if you like, are different, they have to have a different property, but by the principle of identity of indiscernibles. Well, the principle of identity indiscernibles fails. I mean, it's a good principle, but it fails in abstract set theory, and that was a stumbling block for this whole idea. The category theory gets over that altogether simply by not using attributes or the idea that you have individual objects, which you just think because they have an attribute distinguishing them. And that's a completely different approach, which enables this theory of abstract sets, or Cantor's theory of ones, or Cantor's cardinal challenge, have actually an autonomous, if you like, an autonomous foundation. Okay. So in that case, if you take the exponential 2 to the x, right, which would be in concrete sense, they said of all maps from set x to the set 2, in other words, characteristic, usual two-value characteristic functions on x, then this corresponds to the power set of x, right? Because every such map, two-value map, determines uniquely a subset of x, which consists of the places where the characteristic function take the value 1, and that's the usual correspondence. So we get power sets out of this notion. 2 to the x in this case is the positive. I should say, those who are thinking we're topos here, yes, but this is the category classical sets where 2 is the sub-object classifier. In general, and we'll come to that later. But of course, in general, top theory, it isn't the subject object classifier is, of course, just 2. It can be an arbitrary hiding algebra. Doesn't matter here. This is starting here from scratch. Now, we come to my favorite axiom. It's in a double sense. It's the axiom of choice, and it's definitely my axiom of choice, which is a very important principle. We're all familiar with it, but it has turned out to be, and Frankel rightly mentions that it's probably the most discussed axiom in mathematics after Euclid's fifth postulate, after the parallel postulate. And the axiom of choice, of course, is a principle that's had a lot of controversy. We know when Zermelo introduced it in 1904, and then later reformulated it in 1908. And he used it to prove, of course, the well-ordering theorem, which enabled the theory of cardinal numbers to be developed in a Cantorian way, basing it on ordinals. Anyway, the notion of the axiom of choice, stated in terms of maps, I'm sure we're all familiar with it, I'll just mention it. If we call a map epic, if it's right, okay, cancelable rather than left cancelable, that is, in classical set, usual set theory just means it's say a map from X to Y is epic if it's onto surjective in the usual familiar sense of set theory. Then a map is a section, right, of that of this epic map P. If the composite P with S is the identity map on Y. So in other words, you can go select an element on the other side, which when it's reversed maps back to the original element in X. So the usual form of the axiom of choice, I'm sure as you all well know, as I don't know in classical set theory, certainly, where there are many equivalents, which are not equivalent, of course, when you're using intuitionistic logic, but they are classically. Are very many equivalents, and they some are intelligent. I mean, immediately the axiom of choice, which Russell and Whitehead, well, Russell called they called it the multiplicative axiom, in Mathematica, and Russell later used the term in Introduction to Mathematical Philosophy, and later work on foundation. The idea that the axiom of choice, usual way of putting it, of course, is as you have a bunch of abstract, well, a bunch of sets, whether they're concrete or abstract, and you can, and each one of them actually has something in it, so it's not empty. And then there's a map that selects, so to speak, one element from each. It doesn't tell you how to do it. It just says it's there. It's purely the usual. And of course, the interesting thing is that as far as concrete sets are concerned, in the usual sense, the axiom of choice appears obviously true if you don't specify how you actually make the selection. I mean, the whole issue, really, Zermelo there were a lot of objections to the axiom of choice when Zermelo introduced it or formulated it, because unfortunately he did use the term choice, and that is you make a selection as if you could define it. But Zermelo does point out that's not necessary. It's like the Russell shoes and socks. Russell made that point in. You can select, there's a way of selecting shoes from an arbitrary collection of shoes by taking the right shoe and the left shoe or whatever. But in the case of the socks, you can't, because you can't distinguish, right, the socks from one another. Now that's actually an interesting point here, because abstract sets are like socks. They're not like shoes. So Russell's example of the difficulty of trying to make sense or understanding the multiplicative axiom or the axiom of choice by making a selection, by specifying what a selection should be from a bunch of pairs of undifferentiated socks. Well, that's really how the axiom of choice the assumption that can be done, so to speak, that there is such a selection, has to be an intrinsic principle, if you like, of which can also be false. You could produce models in which that's false, and those go back essentially to Frankl, where they actually use atoms. And it's interesting that the formulation of set theory with atoms, these atoms behave very much like they're interesting. They're very similar to the idea of these dots or undifferentiated elements, objects that simply differ by the fact that they're different from other objects. The notion of an atom, of course, has been an interesting notion in set theory. And you get this, I'm sure you're familiar, that the original proofs of the independence of the action of choice were not were with set theory with atoms, which Frankl and Golem actually worked on. And it wasn't, of course, till the 1960s that Paul Curran was able to extend that idea to sets, to arbitrary concrete sets where there are no atoms, and where particularly you could have the axiom of foundation. Okay. Now, the axiom of abstraction is the assertion then that any epic map or set has a section. It could be, so to speak, inverted in that sense, and in that weak sense. And of course, there are usually very many of these sections. The principle is taken to be correct. But why is this principle taken to be correct for abstract sets? Well, because of the totally arbitrary nature of the maps between them. You don't have to specify the map that the maps in abstract set theory, also in concrete set theory, except that maps in concrete are then defined, but it has to be defined as a concrete set. That is as the extension of an attribute. That is, a set of ordered pairs, at least in the usual set theory. But from that, the idea of the axiom of choice being correct for pure sets, so to speak, in this is because the way of selecting element doesn't matter. I mean, as long as that if you can imagine an agent that comes along and picks out an element from each of them, member of a family of non-empty sets, it doesn't matter how. You just like think of them as grab bags, and you don't have to specify how you do it. If you try to make the function, the section or the way of selecting an element from a set definable in some way, then you get a much different version of the axiom. So it's a strong version, which was shown, as you may know. It was shown that in the usual set theories, by I think Ezra Livy in the 60s, that it's consistent to assume that the axiom of choice holds in this in the sense I've just defined, but that that there may be no definable way of making a choice from that. So in particular, it's consistent to assume that there's a well ordering of the real numbers, but there's no definable one, which is a subtle point. Because originally in Russell's work, Russell White's work in Principia, it seems to have been implicit in ramified types that everything was definable. And in fact, this was part of the objection that was made by Ramsey. Ramsey, of course, produced this critique, the famous critique of Principia and of the ramified type theory behind the framework of Principia, that in fact it makes this assumption that all the functions are definable. And Ramsey did have this idea that the axiom of choice is obvious, or he multiplicative axiom is clearly correct. If you don't, it's just undefinability, which has been one of his principal points of his critique. Okay. All right. Well, anyway, there's a diagram here which I can't really show you. I'm sorry I don't have slides, but anyway, you can just see that when you select.
I can demonstrate this diagram.
Yeah, why here? Okay. Well, look. So Just a minute, let me get it again.
I can demonstrate this diagram from my computer. I have your paper.
Oh, you do? Well, do that. Yeah,
Oh,
there it is.
wait.
There it is. What?
Yeah, we see.
You see it? I mean, it's, it's not startling. Okay. Now, that's the axiom of choice. Now, the axiom is just, I'd like, because I have been hipped on the axiom of choice for many years. It is astonishing. I've written a book on it. There's a number of books. It's probably the only axiom. Okay, it's on which several books have been just on the axiom of choice. And it's interesting that how it's come to assume such an important role in the foundations of mathematics. Also, the controversy, which took me, I remember being very puzzled, along with, I wasn't the only one. Of course, it didn't take much to puzzle me, but even so, I was very puzzled when I first started to learn Thomas theory in the 70s. Was about the axiom of choice, and the thing that got me, I just make this anecdotally, but the thing that fascinated me was the theorem proved. It goes back to Diaconescu, who showed essentially that the axiom of choice formulated in this way implies the law of excluded middle. This is a famous result, which was originally proved in a topos or in a category that has enough properties to make it similar to a topos. And then later, of course, it was by Myhill and the other way, Goodman. And Myhill then produced a very nice proof of the axiom of choice implied the law of excluded middle in very simple intuitionistic type theory. Now, that's really quite remarkable that nobody would have dreamed of that result before. Then I thought, well, that's very strange because from what I understand of intuitionistic type, or the axiom of choice is actually provable, right? In intuition, because of the way you define the quantifiers. What? So does that mean that somehow intuitionistic logic collapses? Well, the answer is no, because the interpretation is different. But the second point as to why the axiom of choice is affirmable in many systems of type theory, in particular in basic marginless theory, on the one hand, but it doesn't apply the law of excluded middle there. Well, exactly why? Well, it's turned out to be quite a subtle issue, as I'm sure, as you may well know, and there's been a lot of comment on that. Okay. Anyway, so that's the axiom of choice, and we take it as as a principle that governs set theory, and it's true when you ask a category theorist what he means by the category of sets. Sets are top of satisfying the axiom of choice. And a few other, of course, you might have to add a few more things, but basically what distinguishes the category of sets, the category theorist, is really the fact that it satisfies the axiom. Because very few categories do, as you know, even we'll come to that, even very simple categories violate the axiom of choice in a very natural way. Now, the other important notion, of course, maybe certainly more important, I guess, historically, is the notion of an infinite set. And the idea of actual infinity, of course, motivated much of Cantor's work, the idea of transfinite set theory, if you like. And we, in abstract set, it's very easy to define what an infinite set is. It says an infinite abstract set is infinite if there exists an isomorphism between the set X, set X, and the set X plus 1 obtained by adding an additional dot. In other words, X plus 1 is isomorphic to X. It's a beautiful definition. Of course, it's just a familiar way, a very succinct way, if you like, of expressing the idea that it doesn't matter that it violates, of course, the principle that the whole central thing, that an infinite set is one that violates in some way the principle that the whole is always greater than the part, which of course is Euclid's fifth axiom, and that's the thing that is violated really in set theory, that infinite sets have this property. Now, it was the discovery of Dedekind, of course, in the 19th century, that the existence of an infinite set is equivalent to the existence of a system of natural numbers. I mean, if you've got the right machinery, you can show that if you have any set will give the infinite set will you can carve out, if you like, or define a system of natural numbers, which is also unique up to isomorphism, which is unique up to isomorphism, of course. Given that, thus that leads to what's, of course, the axiom of infinity. And this is assumed to hold in abstract set theory too, at least in the formulation of it that we're looking at here. So the category set is thus supposed to satisfy the following axioms, and these are essentially the axioms of the Lawvere called the elementary theory of the category sets. Have been put slightly differently. There's a terminal object category. Okay. There's a terminal object one. Any pair of objects has a Cartesian product. These are all, of course, given the appropriate definitions of the notions involved. For any pair of objects, you could form the exponential object. There's an object of truth values. Right? I haven't necessarily said it's two, but there's an object, usually written omega, which is such that for each object, there's a natural correspondence, again, essentially involving an adjunction, I share the details here, between some objects of X, or if you like subsets, and arrows or maps from X to omega. Now in set, we can take omega to be the two element set, 0, 1, or if you like, two dots. Secondly, a non-trivial axiom of non-triviality, that the one dot set is not isomorphic to the no dot set. Of course, you could have that, it would just collapse everything to a one object category. I mean, and you don't want that, so you put that in. It's like not having one element Boolean algebras. And the axiom of infinity, which I've just mentioned, that there's an object that is isomorphic to X, which is isomorphic to X plus 1. Of course, you have to define what you mean by plus. I haven't done that. This, of course, is defined. It can be defined as, again, in terms of an adjunction, which I won't go into here. The axiom of choice, and this last axiom, at least for the category of abstract sets, classical abstract sets, the terminal object one, the one dot set, is a separator. That is, it enables you to separate functions or maps by their actions on one. The category satisfying axioms 1 to 6, that is, without the axiom of choice and the well-pointedness axiom, suitably formulated in the first order language of categories, is called an elementary non-degenerate topos with an infinite object, or simply a topos. They now just called a topos. It was called an elementary topos when Lawvere and Tierney first introduced it, building, of course, or simplifying, if you like, the idea that originally came, of course, from Grothendieck, that and which became known as a Grothendieck topos, typically a category of sheaves over topological space, which I'm going to mention briefly later. Now, the objects of so the category of abstract sets is thus a topos satisfying these special additional conditions, namely the axiom of choice and the well-pointed axiom that says that what is a separator, that maps are determined by their actions, if you like, on individual dots. The objects of the category of abstract sets have been conceived as pluralities, this whole idea, which in addition to being discrete, are also static or constant in the sense that the elements undergo no change, so to speak. Now, there are a number of natural category theoretical functions to bringing variation into the picture. And of course, Bill Lawvere's original, when he was first promulgating the idea of hypothesis. He and Miles Tierney years ago. His whole line of a way of understanding what a topos is, it's a category, some kind of category of objects that's undergoing variation. And because variation and constancy played what he would call the dialectic between the two, since he was very fond, of course, of Hegelian terminology. The dialectic between constancy and variation played a central role in his thinking, of course, about categories and the nature of categories. Okay. So there are a number of natural category theoretic approaches to bringing variation into the picture. For example, you can introduce a simple form of what called of discrete variation. Well, variation could be discrete or continuous. This is just discrete. So you actually jump from one value to the next. It doesn't, so to speak, necessarily smoothly. We can introduce the simple form of discrete variation by considering as objects what I called here bivariant sets. That is maps, right? Well, the objects now are maps between abstract sets. Do we think so? So a map, let's say between x0, set abstract set x0 and abstract x1, and you think of x0 as the state of the bivariant set, which is called an f, which is just this function at state 0 or then, and x1, right, the codomain of the function of the map, as the state at stage 1 or now. Well, of course, you could say then and now, right, or now and in the future. So really, it depends on which way you want to look at it, whether you're talking about past or future. I've chosen to think about the first stage as being in the past, and the second stage, if you like, as being now. The bivariant set may be thought of as having undergone by the transition F, that is the map that moves, so to speak, the domain into the codomain, as having undergone via the translation F a change from what it was then, which was x0, to what it is now, x1. Any element x of x0, that is, or of f, becomes the element fx of x0 now. So the map thought of as moving, if you like, an element of the thing, then to become, so to speak, under f an element now. It becomes transformed, so to speak, into that. Any element, okay, pursuing this metaphor, two elements then may become one now, if f is in monic. So if you imagine these two elements then, they're different, they merge, if you like. They become identified in some way. Now they become the same. Pursuing this method, okay, or indeed a new element may arise now because f is a map. No element then can split into two or more or vanish altogether because of course maps are many one, right? Not one many. Now, what are the appropriate maps? The bivariant sets then consist of two-stage sets, if you like. So the objects are now, what are they? Well, a map also is a set of dots, but of course, these are more complicated sets of dots, so to speak, at least from a categorical standpoint. They can be seen as pairs of maps between their, so you have to then define what you mean by the maps or the arrows between these bivariant sets. Well, I'll spare you the details. They're just maps which are compatible, right, with the transition maps. So you imagine you have two of these things. There's one, x0 to x1 and y0 to y1, and then a map between those things is really a commuting square where you move x1 to x0 to y0, and you move x1 to y1, right, by these maps, and then the whole diagram has to commute. So that gives you a category, a very familiar one. Very simple. Bivariant sets of maps between them define this. They form which I call the category BIV of bivariant sets. Now, like I said, you could easily, it's well known that BIV is a topos. It satisfies the basic conditions for being a topos, but the introduction of variation causes several newer features to emerge. Begin with the sub-object classifier omega is not two elements, two dot set anymore. It's actually a bivariant set. I won't describe it. It's actually a map into the two element set. It's one that identifies two of the elements in them. But the map is defined on the three element set. So when you think of the truth value object, it's consisting of three things: 0, right? 1, and then something in between. And this, again, those of you I'm sure familiar with it, there's a bit of topos theory. Well, of course, that's, if you think of it as a hiding algebra there, it's a three-element, it's a very simple hiding algebra consisting of a linear ordering consisting of three elements. So you've added one new stage. And similarly, of course, to, you could do this with you can make it tridiagonal. You could just iterate this idea very simply. But it's a good example. Now, the axioms 5 and 6 continue to hold, but axioms 7 and 8, the axiom of choice fails. It's not very difficult to show that it fails on any of the details here. It's easy enough to show that there are onto maps. Sections. These are the simplest, some of the simplest examples of categories that derive from where the axiom of choice holds to one where it doesn't. And also the idea that this assertion, and one also isn't a separator. Maps are not determined simply by their action on a single dot. And it's not very difficult to prove that. So the axiom of choice and well-pointedness are incompatible with even the most rudimentary form of discrete variation. I mean, that was, of course, Lawvere's point long ago, that the axiom of choice and well-pointed, these are all forcing stasis. And as soon as you introduce any kind of variation, both of these ideas go out the window. The axiom of choice, of course, there are stronger forms of stasis in set theory, not just the axiom of choice. There's a thing called the axiom of constructibility that doesn't really have a very nice formulation in category theoretic terms, but it's certainly very strong as a, essentially every set is definable in a certain way. But at any rate, this idea that the axiom of choice is associated with the idea of constant stasis, and that was a central point, really, of Bill Lawvere's original early work in this area. Okay, now abstract sets can also be subject to continuous variation, and of course, it's continuous variation that is really it's the center of mathematical analysis, calculus, well, geometry too, to some extent, except you don't think exactly of lines as being variable, but you can imagine moving along a line, for example. How do you introduce continuous variation? Well, this in abstract sets. Well, I'll just give you a sketch of it. It's done in the first instance, and the way it's usually done in the first instance, by considering in place of abstract sets. Well, it's really new kinds of abstract sets, but they're abstract sets with some more structure, which you call bundles. A bundle over a topological space. Well, now you can define topological spaces, of course, in category theoretical terms, using the notion of a power set. You can reproduce that definition. And then, but I'll usually use, I'm sure everybody's familiar with the concept of a topological space. And the bundle over a topological space is just a map, continuous map. If it's a bundle over a space, topological space, say X, is just a continuous map, let's say P, from some topological space Y to X. I mean, it's the simplest kind of. And then a bundle, well, you look at the fibers, you look at the inverse images, you imagine there's this map from Y to X, and you imagine the arrows going there, and then you take for each point in Y, sorry, in X, you look at the inverse image, right, of that, and there may be more than one point in it in X, and in Y, and the bundle of all these inverse images is that's why it's called a bundle, of course. It's a term in topology. And we can think of the value, if you like, these fibers or the inverse images of the points in X under this map from Y to continuous map from Y to X. And it could be conceived, a natural way of conceiving it, these bundles as an abstract set varying continuously over X. So you think of you think of X, there's your topological space, and you have all these fibers, right, which are inverse images of the map constituting the bundle, and you think of those as varying over the set, right, X as you move through it. It's a very familiar idea from logical motion. Well, then, okay, so there are your objects of your category. These bundles are also abstractions of a certain kind, but they do. This is how we describe them in the usual mathematical manner. We then have to describe, these then form the objects of a category. What are the maps? Well, again, between two bundles, you have a map between two bundles as a map that respects the same thing. You have X and you have Y and you have Y prime. And you imagine the two bundles, Y over X and Y prime over X, and then a map between these two is considered a map from Y to Y prime, such that when you compose it, right, with the other two maps here, you get a committing triangle. So this is what you call respecting the variation. Bundles over X and maps between them then form category, let's say bun X, the category of bundles over X. And this is, of course, a fundamental category in the categorical approach to topology. Now, while categories of bundles do represent the idea of continuous variation in a weak sense, you might say, well, okay, once I've got bundles, why do I need any more? I mean, why doesn't that simply capture the idea of continuously varying abstraction? Well, there's a reason that it doesn't. I mean, at least maybe with hindsight, I don't know. But they don't satisfy the Toppus axiom. See, there's another problem. The bundles don't form a Toppus. Of course, that's one major problem. There's no object of truth value. And you can't form exponentials. Of course, the problem of not being able to form exponentials in these various categories has been the sort of bane the categorical approach to topology. Cartesian, a category that satisfies, that has Cartesian products and exponentials is called Cartesian closed. And of course, those two principles are absolutely fundamental in approach of abstract mathematics. Well, they call it abstract mathematics in analysis, that you have product spaces and you have spaces of functions. And the whole development of 20th century mathematics, or a lot of it anyway, can be seen for the Hilbert spaces and all the rest, functional analysis and as the use of exponentials as functions being considered as constituting elements of new spaces called function spaces, and hence functionals. But if you don't have those, then it's not the appropriate notion of it's of course it's a weak way, if you like, of it's a rudimentary way of introducing variation, but it doesn't. You can't perform the mathematical operations in the category of bundles over topological space in the way that you can say in the category sets or category of abstract sets. So you've got to find some other way of doing that. I'm this is sort of usual, really, if you like, sort of mixing up the history of this. Is just the history of sheaf theory, as you're coming to, is actually quite complex, and I'm sure you're aware of that because, of course, it was very strongly connected with algebraic geometry, and this is really where most of the development occurred. I mean, through Vey and Serre, and of course, especially later through Grothendieck. Okay. Okay. Now, categories of bundles do represent the idea of continuous variation in a called a weak sense. They fail to satisfy these Thomas axioms, and all fall short of being suitable generalized. And so, sorry, all fall short of being suitable generalizations, where suitable means being able to perform the kind of mathematical operations that mathematicians are familiar with. In other words, the ones you could, a lot of them you could perform in set theory, which is most of the point of set theory anyway. I mean, in practice, still is for most mainstream mathematicians. Okay, so we need to think of another way of going about this. What you might call suitable generalizations of the category of abstract sets to allow for such variation. We have to confine attention to special sorts of bundles. And these bundles are known as sheaves. A bundle over, you have a bundle of y of x over x, y to x. It's called a sheaf. When the map constitutes the bundle, is a local homeomorphism in a sense that each neighborhood, for each point in the domain space, let's say A, there's a little neighborhood, right, in the topological space Y, that under the map P constitutes is homeomorphic to its image, to the neighborhood of the image of A. So in other words, you imagine you have a little neighborhood on one side, and if you take it sufficiently small, then that neighborhood can be translated by P is translated by a homeomorphism to a neighborhood surrounding the image of the original point you started with. So, the domain space of a sheaf over it. Well, again, historically, why do we call that a sheaf? Again, because if you think of these as bundles and inverse images, then you get the idea, right, of the geometric. Of course, the term goes back to the French faisceau, a sheaf. If you look at it in terms of bundles, it's supposed to look like, so to speak, a bundle of stalks, whether you might think of them as spaghetti or wheat sheaves. And of course, it just shows, this very amusing, mathematicians pointed out the very agricultural, the centrality of agriculture, in French culture, French society, where a lot of the terminology for this comes from the farmyard, right? Sheaves and bundles and packs and so forth. Anyway, okay. All right. So the domain space of a sheaf over X locally resembles X in some sense, in the same sense as a differentiable manifold locally resembles Euclidean space. Of course, that was part of the idea of a sheaf. I mean, the idea of Riemannian manifold, of course, goes back to the 19th century, and the Riemannian manifold is you can formulate in sheaf theoretic terms. It's one that actually has a stronger property than the sheaf over Euclidean spaces, right? That it has metrizability conditions too. But essentially, these neighborhoods, the idea is that a sheaf, the codomain space resembles the domain space locally sufficient that you can think of this being patched together, if you like, from neighborhoods in the original domain space. And similarly, with a Riemannian manifold, you can think of it as in some way, being patched together from little copies, right, of Euclidean space. It's not necessarily all of the same dimension, but the idea is the same. All right. Okay, it can then be shown the category sheaves over X, of sheaves over a given topological space, and maps between them as bundles is a topos. That's a topos. It's a beautiful theorem, of course. It's taken sort of for granted now, but that it's a sheave, a category over it's a category automatically, but it's actually it's a topos. A category of sheaves in general is called a Grothendieck topos. This was his generalization of the notion of a topological space. I'm getting a special offer here that I don't want. Oh, yeah. And that's what really, I just mentioned the centrality of that. The whole topos theory really comes from Grothendieck's generalization of category of sheaves. I mean, the notion that a sheaf, you don't have to be just over a topological space. Grothendieck, as I'm sure you know, replaced the notion of a topological space with another category, namely the category of open sets, right? And then it's a category of open sets of the space is replaced by an arbitrary small category. And then you get the idea of a category, as he called this, a site. And then the category, he generalized the notion of a category of sheaves over a site. And that's what he called a topos. This was now it's called a Grothendieck topos. And there were characterizations of abstract or mathematical characterizations of categories that had the property of being categories. So it's called Giraud's theorem. It's a very big theorem at one time anyway. I don't know whether it's so important. But it certainly was in the sort of early days of. And I should also mention, Grothendieck did regard, I mean, you know, he became, say, rather somewhat eccentric in his later years, as I think we all know. But he still says, I mean, you can see in some of his letters and so on, he was justifiably proud of the concept of topos. I mean, of course, he was self-fertile as his mathematical imagination, of course, was vast, you know, gargantuan. But the notion of the topos did occupy a very special place in his thinking. As I said, I think I may have mentioned it, when Lawvere and Tierney came up with the idea of elementary topos, which Grothendieck was also impressed with. And you know, what he didn't have, because he didn't really care for logic all that much, he did not see the idea of a sub-object classifier. And he said so. He said, well, you know, Lawvere and Tierney had this. I never noticed the presence. I was sort of really interested in Cartesian closeness. I didn't think of it in terms of sub-object classifiers and truth value, because he wasn't, you know, the French never cared for mathematical logic all that much. But I think that's changed. But right back to the days of Poincaré, I mean, he thought it would maybe a waste of time, even though he had very strong philosophical insights himself. Anyway. So here we are. So it's the category of sheaves is a topos, and the more general one, where you could replace the category of topological spaces by by an arbitrary small category, which Grothendieck called the site, and then you have to have a certain way. The central idea there really is idea of coverings. I won't go into this. I'm sure you're familiar with it, because the axis for sheaves, really one of the important aspects of sheaves is that you can construct sheaves by being given them locally. That is, where you have a covering of a given topological space by a bunch of open sets. That if you know what the restriction, if you have the right compatibility conditions and you give a sort of local definition of a sheaf in each neighborhood or each open set, you can fit them all together to form a sheaf. And that's, of course, a characteristic axiom for the one of the defining principles of sheaves. And Grothendieck uses this, generalizes that idea to the idea of an abstract covering for a category, which he called a site, and then we get the category of sheaves in that sense, which is a very important note, which again led to his idea, it's connected with his idea of schemes, and so on. I should just mention, though, since I have I'm really should thank you for your indulgence here, but it's very interesting that of course, if you approached all this stuff of sheaf theory and so on, I mean, as a logician, it was natural for me, even though I didn't start as a logician, but it was natural for me to think of trying to think of Thomas's in a kind of logical way, and they're very important aspects of Thomas theory, the internal language and the internal intuitionistic logic and so on. But of course, it's not true that Thomas theory or the idea really came from set theory. It didn't. It is amazing that it turned out that Thomas theory was a kind of generalization of set theory, but that wasn't what Grundig was thinking of. It was really Bill Lawvere who thought of that. But it is remarkable that it turned out that you can really start essentially with a logical approach. I wrote a whole book on it called Thomas's and Local Set Theories back, I don't know, whenever it was, a long time ago, Middle Ages. I have to say that book is at least, it achieved the distinction of being republished by Dover Books, which of course I think is the ultimate accolade, for a mathematical author. Anyway, but the thing is that that's really the source of Thomas theory. It was realized, the people in algebraic geometry and didn't care for logic. Grundig didn't know any and wasn't terribly interested. And then the extraordinary thing was that when Paul Cohen and Grothendieck, of course, had the Fields Medal, 1966, won Fields Medal in the same year. That was the last year in which I could understand some of the work of these people. Well, Cohen, of course, because of forcing and so on, which I worked in. And then later, some of the work of Grothendieck in not really deep algebraic geometry, but in terms of hypotheses and so on. And the extraordinary thing was that within a few years, or very soon after that, Lawvere showed that the Cohen forcing is a special case of sheaf theoretic. Cohen's construction can be shown to be a special case of what Grothendieck was doing, although neither knew. I think it testifies amazingly to Cohen's originality. He didn't know. It's true that he did know a lot of mathematics, but the fact that Cohen forcing and the independence of continuum hypothesis can all be represented in terms of sheaf construction, I think an extraordinary development. Very, very beautiful. Okay. So the truth, just to mention it, the truth value object. So this category sheaf has a truth value object in the case of topological spaces, a thing we're using them. And what are the elements there of the abstract or the set constituting the truth value? Well, guess what? It's just the topology. It's the collection of open sets of the space, which of course is well known to be a hiding algebra. And it's well known to play a role in intuitionistic mathematics because Tarski, I guess it goes back to Tarski in the 1940s and Birkhoff, both knew that you could model intuitionistic logic or within categories of within topological spaces. So that goes back quite a long way. Okay, so categories of sheaves are the appropriate generalizations of the category of abstract sets to allow for continuous variation. This is sort of generally agreed by mathematicians with these areas. And the term continuously varying set is taken to be synonymous with the term sheaf. In general, both the axiom of choice and the axiom of well-pointedness fail in sheaf categories. It's not very difficult to do that. There's a familiar example of a map you can't invert, which is you take the circle, then you take the double covering of the circle, and you have a natural projection onto the circle, but you can't invert it in the category of sheaves. It's a standard example. I mean, you find it in all the. So, both principles, the axiom of choice and well-pointedness, are incompatible with continuous variation. So it's incompatible both with discrete variation and continuous variation. Well, in other words, with variation in general. That's why the axiom of choice is the axiom It's kind of par excellence that characterizes the idea of a kind of static universe consisting of, if you like, of static objects that don't change. Now, if we were to take X to be a space, right, so we started this topological space, consisting of a single point, what's a sheaf over X? Well, it's a discrete space. It's easy to see, a space in which every subpoints are open, or sequences are open, in which right, every subset is open. The category of sheaves over X, right, where X is a single point, a single dot, is essentially the category of abstract sets. So that's how you recapture the category of abstract sets from the category of continuously varying abstract sets. The category of static sets, you just stop the variation. You just locate it as a single point. So in other words, an abstract set varying continuously over a one-point space is just a constant abstract set. In this way, arresting continuous variation leads back to constant discreteness. Now, you might ask what happens if you chose categories of bundles to represent continuous variation. I mean, suppose, why not? It may not be a topos, but you can certainly do nice categorical tricks with it. Well, then, in that case, if you use just arbitrary bundles rather than the special bundles which are sheaves, then the constant variation, right, over a one-point space, would lead not to the category of abstract sets, constant discreteness, but to the category of topological spaces itself, which is another category that doesn't have very nice properties. The category of topological spaces itself has never been one that it's not Cartesian closed. Of course, it's a very natural definition of set theory, but from a category theoretic point of view, it has its difficulties. That's one reason why the category of sheaves, if you think of category sheaves as Grundig thought of a category of sheaves as a category of generalized topological spaces. That's the way he saw them. And those space that category has all the nice properties that the category of sets has. Not that he was thinking about the category of sets explicitly. Category of topological spaces, on the other hand, as a category, has never been terribly satisfactory. There have been a lot of efforts to. I mean, it's pretty well understood now, but in the old days, they were trying to make. They were compact. There were various attempts to make it Cartesian closed. Rusty on this, so I can't remember the details. Okay, you would get the category. So what you might call constant continuity. I mean, topological spaces already embody itself in themselves an idea of continuity, but it's constant continuity. That's the only way you can. It's another way, maybe, of thinking of topological objects in the category of topological space. So this is another reason for not using a bundle category to the criminalization of the category of abstract. Right now, I'm nearly finished here. You'll be probably believed. All right. Now, there's an alternative description of sheaf categories, which brings forth their character categories of variable sets even more strikingly. For sheaf X, it's a beautiful theorem, right? I don't know who first proved it. Maybe it goes back to Jean Lawvere, I mean, who invented the concept of sheaf. You know, he was you know that. Jean Lawvere was a prisoner of war during the Second World War, the Germans. And he worked out the category of sheaf, the idea of a sheaf and so on. He was in prison camp for most of the Second World War when he came out. It wasn't as if the notion of sheaf, came fully formed from his forehead, but he'd had plenty of time to think about it. Yeah. Or you can think of sheaf X as a category of sets as varying over open sets in X. So it's a category of variable sets in that sense. There's a well-known theorem that correlates variation over open sets, it satisfied the right conditions and sheaves. It's one of the first theorems you see when you're working sheaf theory. It's in McLean and Moerdijk. It's probably page 2 in Johnston's formidable. I don't mean the elephant. I mean his first book on topos theory, which is just called Topos Theory, which he published in 1977, which is a very difficult book. Varying over open sets of X. So, right, that's what we think of it. You could visualize it. I've already given the idea of how to visualize it. I'm familiar with it. You think of these stalks, like the inverse images, and these vary depending on the point. You could have stalks of varying length, for example, in a wheat sheaf. This type of variation could be further generalized to reduce categories of sets, varying over a small category. Well, I've already mentioned that's what Grothendieck was doing. Each such category is again a topic. Further refinements of this procedure yield so-called smooth toposes, categories of variable sets in which the form of variation is honed from mere continuity into smoothness that is arbitrarily many times differentiable. Smooth infinitesimal analysis emerges from this. I've written a modest little book called The Primer of Infinitesimal Analysis on how you can do infinitesimal analysis using these ideas. Regarded as universals of discourse, in a smooth topos, all maps between spaces are smooth. In other words, it's essentially it's the world of classical physics. The fact that calculus worked so well, right, for classical mathematical physics is because of the assumption, essentially, that all maps are smooth or differentiable. If they aren't, regarded as as universals of discourse in a smooth topic. But again, there's a way of thinking about that. It's more complicated. But as sets varying, you have to do a lot more constructions to get it. Look at, you want the full details, look at Mordyke and Reyes's book, which is tour de force. Models of smooth infinitesimal analysis, beautiful, difficult. Anyway, that's the basic idea. So smooth topos, all maps between spaces are smooth arbitrarily many times. They'll see infinity. Even more remarkably, the objects in a smooth topos can be seen as being generated by the motions of an infinitesimal object, a generic tangent vector, because it turns out that these they're representable by classical notions that weren't very precise in the 19th century. That is, things are called tangent vectors, which of course don't really exist in the sense of objects in classical mathematics. It's inconsistent. But it's consistent with intuitionistic logic. And as you may know, essentially it's consistent with the idea of infinitesimals, which are nilpotent, that is, they have squares, which are not zero, or at least you can't prove that they're zero, but whose squares are zero, which again is not a classically notion. Although the idea of that idea does go back. Leibniz and a Dutch mathematician called Neuventijk had the idea that back in the 17th century that an infinitesimal can be considered as something that's so small that it may not vanish itself, but its square does. And of course, that idea is the one that engineers have been using for long. Simply assuming, in other words, the Taylor expansion of a function. You just ignore the terms of square and higher. And of course, that's a typical way engineers used to do things. This is envisioned by founders of differential geometry. I suppose the idea goes maybe not to the infinitesimals, infinitesimal, but the idea of tangent vectors conceived in this sense really does go back to Gauss and Riemann. So, starting with the category of abstract sets and subjecting its objects to increasingly strong forms of variation leads from discreetness to continuity to smoothness. The resulting unification of the continuous and the discrete is one of the most startling and far-reaching achievements of the categorical approach to mathematics. Well, thank you very much.
Yep, Professor Bell, thank you for a talk. So we have some time for question. So if someone have a question,
It's just time for me to answer them. That's a question.
yeah, thank
Yeah,
you.
sure, of course. course.
So if someone have a question, you can just raise your hand and
Yeah,
Zoom.
you can ask me anything. I won't answer it, but I'll provide you with some kind of answer.
Probably there are some questions from
Sure.
people in the room. So thank you. The first question.
Uh, Thank you for the talk. It was very illuminating, especially the story about socks. It really made my day.
Yes, the socks.
So my question is it possible to map an abstract set to a subset of natural numbers? And if so, can structure be forced upon an abstract set using this mapping?
Well, I wouldn't think in particular in the case of, but you can. There are various theorems that tell you that you can, if you have to add some somewhat more conditions. Um, but the notion of using, if you take the category set of abstract sets, just think of it as a topos and use its internal language, then you get something that really does look like set theory. I mean, you could introduce the language of set theory with the appropriate notion of a collection of objects, of things satisfying a particular attribute. And so therefore, yes, in the case of the natural numbers, once you introduce the natural numbers, then you can define subsets of the natural numbers within the internal language, right, of the topos. Now, what sets are definable there exactly? Of course, in set theory, there's an issue about you have to characterize what sets of natural numbers are actually definable in the appropriate way within this within that framework. But the short answer then is yes, you can mimic, if you like, using the appropriate formalism, the definition of the set theoretical language, the notion of an attribute, and the extension of an attribute. The only you could do that in an arbitrary topos. It's called the language, which was developed back in the 70s. And so I guess the answer, as I said, your question is yes. But again, the exact connection between the set theory that you do in a topos and the set theory that you do in the usual set theories, where you actually have, in a certain sense, a lot more, if you like, instruments, if you like, for defining things than you do in the internal language. Well, why? Because in the case of the internal language of a topos, it's local. There are no unbounded quantifiers. Right? You can't say, I mean, one of the things about the classical set theory, of course, the thing that led to difficulties with it, perhaps, is the fact that you could take any property defined on the whole universe of sets and say, let's define the set of natural numbers, for example, that constitutes you get Tarski's undefinability theorem this way. The set of natural numbers that constitutes the Gödel numbers of true sentences of arithmetic. Well, what does true mean? Well, it means true in the universe of sets. So what you're doing essentially is talking about the whole universe. Now, you can't do that, at least not in the local set. Well, I called it local set theory. The corresponding set theory, which looks like set theory, but it's only defined locally. So therefore, there is a difference. But certainly for properties, notions of natural numbers that don't require definitions over the whole universe, in other words, which are localizable to, well, in other words, there would be like properties that Zermelo considers, in the action of separation. That is, if you bound the quantifier by bound to quantifier, so for all x, you mean you're given a set A such that you're considering not just arbitrary x over the whole universe, but just the sets, the x's that are in A. Yes, you can do that, but you can't talk about arbitrary. And I don't know. I'm not quite sure now. I don't think that's an area that was thought about quite a lot in the past. It's not a major thing now, but there was at one time a lot of work that was done trying to really pin down the exact relationship between set theory, well, okay, between set theory, as I put it, an abstract set theory, that is categorical set theory. But it's true that you have to get used to it. I mean, the fact you can't make definitions. There's another issue. I just relate to it. The other thing, of course, is impredicativity, and I have mentioned that. But of course, in type theories, one of the major issues is that many of the type theories are predicative, that you can't quantify, if you like, over arbitrary subsets. Where if you can, you get impredicative definitions, and that's what. So again, but in topos theory, it is impredicative. There's a thing called predicative topos theory, which, of course, has been worked out really, perhaps more in connection with predicative type theories that emerged since Martin Luth developed them, some time ago. I'm sorry, I don't know whether that really answers your question. I didn't guarantee to answer your question exactly, did I?
Well, I think you have answered much more than my question.
Yeah, exactly.
Thank you.
Thanks. The question from Professor Rodin.
Okay, thank you, John. John, I actually I have a question about. It's actually kind of idea I'm trying to play along, and it sounds similar, and I really want to learn your view and opinion. So this is about what I believe, right? Could be analogy between this notion of internal logic in a topos, right? And developing, as you call it, locally, set theory, other things. And yes, and say the idea which emerged in 19th century, not earlier, I think, of intrinsic geometry of manifolds, which basically, belongs to Riemann, first of all, maybe perhaps even Gauss before, right? So, yes, one thing, how wide it goes, and if we take that kind of seriously, right, it looks like, first thing, in geometry at least, we don't need any external framework, right? We can describe geometry purely internally, right? Would it work somehow for topos? Could we describe topos in its own internal language? So something of that sort.
Oh yes, but I wrote a paper on that.
Really? Which? I tried to read your papers.
Well, I published it in the Synthesis. It's called From Absolute to Local Mathematics.
Yeah. Well, I know that your paper is one of the first papers I got. Yes.
No, that is the idea. That
I should reread it. Right.
Well, I mean, the idea was that there isn't an absolute. Yes, exactly the idea. There's no absolute geometry.
And then I think
it's
really
an absolute. Yeah. No, I like the analogy. I'm not sure what.
Great. Yeah. No, that book I actually read. I remember before I met Bill. I met Bill in 1998 in Buffalo, and before I was sitting in Columbia University in the library, and I was reading that paper of yours. But actually, I think
I'm flattered. I'm really flattered.
but I really believe it's something not digested yet, say philosophically, because because it's really changes a lot of things. I mean, if we have this perspective, I probably might call it Hilbertian, or at least its usual interpretation, right? That we have kind of absolute logical framework. It probably may change it. Maybe we may choose it be intuitionistic, but anyway, it's something like external thing in which we may do different things, but it's quite different idea. It's one that thinks may be intrinsic, but even more than there is kind of things become relational in a sense, right? That we may say take one topos, define another set theory, and
that's right,
and so on.
Well, I was looking. I did. The analogy I made, for better or worse, in that old paper, was really was invariant. It was really with general relativity. I mean, the idea. What you actually have is, Einstein's idea that somehow all the laws of nature, you see, the basic things should be invariant under these arbitrary changes, changing coordinates. I had that idea in the back of my head when I thought of the, a topos, say, as a local framework for doing mathematics, and then the parts that are really, when you're looking at the whole, what is true of all, if you like, of these frameworks, has to be the things that are invariant or things that don't change under the appropriate maps. Well, what maps you're going to use? You're not going to use logic. Actually, with geometric morphisms, right, between toposes. Now, if you ask, well, yes, but of course that is the geometric basis for it. I mean, of course, it's true that there was a triumph. Einstein's general relativity, of course, came to the triumph about his thinking of principal privilege and so on. But the idea that it was looking for something where something doesn't change. What you're searching for is what's actually independently of how you're sort of located in it, or what the local, the local conditions are. Well, of course, that's what the basis of general. And I thought it would be a nice way of thinking about what are the laws of universal laws of mathematics. Well, okay, I got Colin McClarty, very good. He shot me down in a review. Said, "Well, that's all very nice, but there's certain problems with this, because there's certain. It is true. I probably carried the analogy maybe too far, but nonetheless, that's the idea I had in mind, was precisely this geometry. Now, you then ask, of course, all these local frameworks. I mean, it's the same with the relationship, let's say, between general relativity and cosmology. You have an actual huge universe. Okay, let's agree, it exists objectively. Who knows what its large-scale topological structure is? Still not really known. It's difficult to see exactly how you find that out. But similarly, it would have a problem here that you have to consider now the category of all toposes. You see, then the equivalent of the cosmos area is that category. I don't think there are any actually, that nobody, it's a category, but Johnston works out. I was never able to, personally, I didn't have the technical competence really to deal with two categories, let alone the infinity categories that they're working with now. But no, that was the idea, that then you see these organs, but they have to fit together in a certain way, right? In order to see what the large scale structure is. Now that may be it's not a topos, whatever it is.
Right? At least in geometry, actually, it, my understanding, right? It kind of relativizes the notion what is an object in a space and what is a space. And but ultimately it goes back to Aristotle, Aristotle's definition of a place, topos, exactly, right?
Yeah, right, sure.
Yeah, he says this is a kind of what is the English word? Kind of enveloping body. So very basically, good. For Aristotle, topos is another body, right? So it's relation. Yeah. And that's why later Leibniz, he would refer to Aristotle as kind of debating against Clarke, against
yes. But I mean the picture I had was but it was the whole debate. There was that's the geometric. You put your finger on the geometric, of course. Actually, there's that issue that goes back to models of set theory, which is where I originally came from. Okay. The Skolem paradox and all that. I mean, there are notions in set theory that are simply not absolute. I mean, the notion of the power set. Unless you're a complete Platonist, which I'm not, I think I've long likened Platonism to disease, like measles, which one should definitely be exposed to in one's youth so as to acquire an immunity.
But different is that
later life, right?
Yes, that classical set theories, they would say, okay, right. There is a mess in the model theory, but there is a kind of absolute logic.
Yes, and that's what's wrong with it. But nevertheless, I think you had to have had it, you see, in order to really see what's objectionable. It's like recovering from some. Oh, well, anyway, but there was that issue, of course, about, well, how do we really know? That goes back a long way. It goes back to Skolem. He then identified, what do we mean by the absolute power of the continuum? He already pointed out that, at least in first order theories, well, he identified as a language, you don't have absolute there. It's not an absolute notion. Now, of course, the people who really think they're ones, it's interesting in philosophy of set theory that there are ones who really think that there is an absolute universal set. Mostovsky didn't. I know, because I didn't know him very well, but we did talk about this today. I didn't believe it. Trotsky never mentions it. Trotsky's very careful for himself. You never really know exactly what it was he believed. He just got these incredible results. Anyway, and Paul Cohen, they all claim to be formalists. Cohen claims to be a formalist. Abraham Robinson claimed to be a formalist. Now, what does this mean? Well, basically, it meant that they don't think that these actual infinities have absolute values. So, in other words, what is the power set of the natural numbers? What is it? In order to describe it, you have to describe the whole universe. It's all things which could conceivably be collections of natural numbers. Yeah, but since you don't have a real way of characterizing the whole, that notion is really relative. And of course, it's precisely that leads to it makes model theory of set theory so interesting. So that's the other source, that you have a lot of somehow local models. In this case, the usual one would be, well, it's essentially what much later, what's his name, very good logician, Joel David Hampkins. Now, Hampkins has been doing, I pointed out to him, I don't know him well, but I mentioned him, and I said, he's been talking, about the universe, about pluralism and set theory. Well, I've been an advocate of that for many years. But of course, the models he's looking at, and he's done some beautiful work in it, characterizes different. He doesn't think there's an absolute universe. They are local in some way, but these are models essentially or models of set theory, models of set theory. He's produced this extraordinary classification and characterizing models that you can get by forcing, intrinsic. Very nice. Well, this is before this is long before he showed up in the scene. But my idea was, well, these are static models. Why don't they introduce variation and use Thomas's instead of models of set theory?
But also people like Schellach and Woodin, they are not impressed by.
No, I know that.
Right.
Couldn't care less, but no, I put admiration for Schellach. I mean, incredible.
Yeah.
I did write to him. He never answered my question. He couldn't, but he could probably. All these are questions about independence of the axiom of choice. I used to work in that, and I still got an open problem. Is the axiom of choice independent? It is a classical set. It's certainly intuition is theory. It's much easier to prove independent since the theory is so much weaker. Is the Sikorsky, is the injectivity of complete Boolean, is the axiom of choice independently of the well-known theorem of Sikorsky, I think it was, that the complete Boolean algebra is injective. Open question. Anyway, that's okay. But no, I did have a little. Schellach didn't. Of course, this is a minor problem for Schellach who's doing these huge things. But yes, it's true. But then there is this view. It's completely different. That set theory is somehow absolute. I don't believe that anymore. I think the notion of it's actually a perfectly. Is it a perfectly common notion? Well, there are problems precisely because you can't characterize infinite sets completely. So, well, up to isomorphism, yes. But the idea that the universe of mathematics is a universe of sets, I don't believe that anymore. It's an important, if you like, representation. And also, it's a complete reduction of the continuous to the discrete. And I don't think that, I think that's a fundamental opposition, one of the fundamental oppositions. As fundamental as one and many, right? Go back to the ancient Greeks, Aristotle, so on. And set theory does represent a real triumph, you have to say, not without its controversies and difficulties, but continuous to the discrete. And I don't think continuity. I think continuity is fundamental. I agree with René Thom.
Okay.
So the geometric part, that's the interesting thing. That when you think of geometry, classical geometry. you know, you do Euclidean geometry, you don't think of this variation. I mean, it's sort of implicitly, you know, when you say two triangles are congruent, you sort of have to imagine one being put on top of the other, and that means, but you know, that's all been, it's not mentioned explicitly, of course, in Euclid, but it's sort of implied that you can make it coincide, and that's what isomorphism, two objects coincide. But the idea of introducing, when geometry is expanded through the calculus, really, to introduce motion, and motion was, after all, the main thing the Greeks, a proper theory of motion is one thing they lacked.
Right.
They had look at the theory of integration, so they had that. Oh yeah, goes right back, you know, the method of exhaustion. It's brilliant. But did they have a definition of the derivatives? No. I mean, it's very subtle that that's the one thing they missed. And you introduce variation. I mean, it seemed natural to me since I got hooked on the, you know, when I first learned Topic theory in the early 70s, about this idea of thinking, because that's how Bill used to, you know, present a lot of this so-called elementary approach to. Anyway, that you think of the topics in some way as allowing variation, you know, within what were taken to be static objects, and of course classical analysis was based on it's a triumph of the analysis of motion, and then if you get the right framework, you can actually put infinitesimals back in. You can do amazing things, and it means that all those things that are classically fictitious, because they're inconsistent with classical logic. That's why. They're inconsistent, in other words, with the logic of stasis. And so these dialecticians, so they never look. There was a huge effort, you know, in the Soviet Union years ago. I remember reading Yenko people. Very, very interesting. They never did produce a satisfactory dialectical logic. I believe it.
Sure.
No, I'm not saying that it wasn't an honorable one, but everybody thought, right, that the real sort of is all the idea of being driven by the idea of contradiction, of actual contradiction. I think that's a marvelous idea. But I don't think, I'm Graham Priest doing all this. I'm not personally convinced by paraconsistent logic. I mean, you could do it formally, but I don't know what negation means if you don't have the law of non-contradiction. What does it mean? Well, you can well understand negation still means, well, a perfectly good meaning when you don't have the law of excluded middle. Actually, that's my view. But then maybe I'm just old-fashioned.
Dear participants, is there any other question? Probably in Zoom. So if there is not, I think we can stop on it. So, dear Professor Bell, thank you again for visiting us. By the way, this online format, it was really, really nice. So many thanks.
Okay, that was a great pleasure for me. Will this be on YouTube or somewhere?
Yeah, it will be on YouTube.
Okay.
If you may. Yep.
All right. Well, no, thank you very much. It's been great fun for me, and as an old man, you know. I'm not yesterday's man, right? I'm yesterday's man.
Yeah.
I'm not sure how that could be iterated. I mean, of course, I'm that old.
No.
Right.
Okay, thank you very much. It's been a great
Thank you,
Have
John.
a nice day.
Really great, really great.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Bye.